For decades, the entire field of astrobiology has operated on a single, powerful assumption. To find alien life, we need to find Earth 2.0. We use our own blue marble as the absolute gold standard, scanning the galaxy for planets with the exact same temperature, size, and atmospheric chemistry. But looking at the math, Earth actually has several biological bottlenecks. Our planet is relatively young, our atmosphere is somewhat thin, and our star burns out quickly. Earth might actually be a mediocre environment for life. In 2020, astrobiologists tested this exact theory by feeding new, optimized parameters into their models. They stopped looking for Earth clones and instead searched for planets with statistically better conditions for biological growth. They immediately identified 24 exoplanets that mathematically outclassed Earth on almost every metric. If we want to find biological entities out there in the dark, we have to drop our hometown bias. We need to look at the super habitable blueprint, the specific physical criteria that make a world objectively better than our own. The first constraint on life as we know it is time. Our sun is a yellow dwarf star, which means it will burn through its fuel in roughly 10 billion years. Complex life on Earth took about 4 billion years to appear, meaning our solar system only provides a very tight, fleeting window for evolution to do its work. But the universe offers a much more stable alternative: red dwarf stars. These stars are significantly smaller and burn much cooler than our sun, which means they consume their internal fuel reserves at an incredibly slow rate. This animated timeline compares the two. A yellow dwarf like ours caps out at about 10 billion years, but a red dwarf can easily burn continuously for up to 70 billion years. The mathematical consequence of that chart is massive. A planet orbiting a red dwarf could easily be 5 to 8 billion years older than Earth. That gives biological evolution a multi-billion-year head start to solve problems, adapt to extremes, and develop complex ecosystems. In the brutal math of cosmic survival, deep time is the ultimate advantage. The second criterion for superhabitability is planetary mass. Earth's relatively small physical size limits how much gravity it generates, which limits how densely it can pack its atmospheric gases. Look at Kepler 452b, an exoplanet located 1,800 light-years away. It sits right in its star's habitable zone, but it is roughly 60% more massive than Earth. That extra mass triggers a physical chain reaction. The planet generates a much stronger gravitational pull, which physically drags the atmospheric gases down toward the dirt. This creates a highly stable, incredibly dense sky, offering excellent protection against cosmic radiation. If a human being stepped onto Kepler 452b, that same gravity would be instantly lethal. Our hearts aren't engineered to pump blood against that kind of downward force. Blood pressure would spike wildly, and the risk of a fatal stroke would be almost immediate. But native evolution would exploit this dense air. Instead of heavy bones and dense muscle, a high-gravity, thick atmosphere environment highly favors buoyant, balloon-like biological entities that can float and swim through the thick gas, bypassing the crushing gravity on the ground. Immense gravity doesn't crush the potential for life. It forces biological matter to engineer radical, non-human designs. This top-down schematic shows a phenomenon known as tidal locking, the third superhabitable criterion. The planet does not spin evenly on its axis. Instead, one hemisphere permanently faces its star, while the other faces the cold void of deep space. This orbital lock creates two extreme physical environments. The sun-facing side is a boiling, irradiated desert, completely stripped of moisture. The dark side is an absolute frozen wasteland, gripped by permanent Antarctica-level temperatures. But right on the border where these two hemispheres meet is the twilight zone. Here, the clashing extremes cancel each other out, creating a permanent, perfectly balanced strip of habitable climate that wraps entirely around the planet. We are watching this exact orbital phenomenon play out right now on exoplanets in the TRAPPIST-1 system, as well as on Gliese 667cc. Life does not require a globally comfortable planet. It only needs a narrow, highly stable perimeter to thrive. We don't even need to look thousands of light years away to find bizarre, habitable environments. We can look in our own local neighborhood. Take Jupiter's second largest moon, Callisto. Initially classified as a dead rock, its heavily cratered frozen surface is an illusion. Beneath that thick ice shell sits a vast liquid underground ocean, shielded entirely from Jupiter's massive radiation belts. Then there's Saturn's moon Titan. It looks like an opaque, featureless sphere because it is smothered in a thick, nitrogen-rich atmosphere. Below those clouds, it hosts a completely alien chemistry, with rivers and lakes made entirely of liquid methane and ethane instead of water. When the Cassini probe analyzed Titan's atmosphere, its instruments detected anomalous data. Hydrogen was mysteriously disappearing near the surface, and nitrogen levels were shifting in ways that geology alone couldn't easily explain. These specific chemical anomalies exactly mimic the metabolic cycles of certain microbes found right here on Earth. The data confirms that biological life does not strictly require Earth's exact recipe of oxygen and water to function. We've mapped heavy gravity worlds with skies thick enough to swim through, permanently shadowed twilight strips, and moons driven by methane lakes. Across these environments, evolution acts as a relentless mechanism of adaptation, shaping biological matter to solve the specific chemical and physical problems of its surroundings. Roughly 3.7 billion years ago, the Earth did not look like the Earth we know. It had a highly toxic, methane-choked atmosphere. It was a harsh, volatile rock that looked remarkably similar to Titan's current state. To the oxygen-breathing life living here right now, the ancient Earth was a completely hostile, lethal alien world. Our planet represents one data point in a massive evolutionary timeline, a world that has spent the majority of its history looking nothing like the planet we recognize.